Welcome back, everyone. So my name is Christian from Essex Startups. Welcome to the fifth day of AI Week and the very final session of the whole series. Much like I mentioned each and every single session before this, please feel free to participate by using either the chat function or the Q&A function. We'll respond to the questions either throughout the session. If we can't answer them throughout the session, we'll just leave them to the end. Today with me, we've got Gustavo from Spotify, who'll be telling us a bit more about understanding our customers through clustering techniques. Gustavo, would you like to take it away?
Yeah, of course. Hello, everyone. As Christian said, I'm Gustavo. I'm a data scientist at Spotify. And let's say that what I want to take you through is not just a fact of understanding audiences. It's what goes through the mind of a data scientist when we're looking at data and why we do these things and how we end up doing what we do. And I'm going to use the context of understanding audiences to take you through that trip. And before I show you anything at all, if there's one thing that I want you to take away from this presentation is that machine learning can be a good thing if it does the right things for the right reasons. So anybody can do machine learning. It's very easy. Now it's just importing and writing 2 lines of code and you get out something. But understanding why, that is a very important thing, so that you don't go into biases and stuff like that. You want to protect your users and you want to do the right thing. And that's been my job at Spotify for the past almost 4 years, is making sure that our machine learning makes sense in the sense of for data scientists in terms of analysis. So with that, I'll start with the presentation. It's called recursive interpretable clustering, which is a mouthful, but it's basically we get data, we cluster it, we interpret it. So I will show you a picture right now. That is a very complex thing, first thing. So I'll take you through all of this and I'll share this same picture again later. So the idea is that we get some data, that's our input. We do something to it to get a low dimensionality representation. And then we do this thing called recursive HTB scan. I will take you through what that means, but it's basically clustering done in a different way. And then we get some results that we try to interpret by doing some machine learning. And then as an output, we get the clusters, which are our audiences that we will try to understand further. So let's go step by step. The first thing that you usually are taught to do when you do any sort of analysis is look at your data. And the way to look at your data is usually by dimensionality reduction. It's the only way. Imagine that you have a set with a few million users, which in the Spotify case, it's a couple hours during the day. And you gather as much information as you can. So let's say you have a few hundred features of those users. And you want to understand that your data is okay, and you want to understand that there's something there. So the first thing you will do is dimensionality reduction. And if you've been studying dimensionality reduction at university or wherever, you probably have some examples of what is dimensionality reduction. I keep saying that the earliest example of dimensionality reduction are paintings, trying to capture a person in a painting, and then we learned to do photography, where we get this 4-dimensional world because there's a little bit of time and you capture a little bit of light into this 2-dimensional thing called a plaque or something. So yeah, then you do PCA. PCA, principal component analysis. Everybody probably has studied what PCA is. it's a mouthful again. It's trying to find axes, whatever. You're basically getting something and you're rotating it to understand what it is. Let's imagine I show you this thing. It's a slab. You don't know what it is because I'm not showing it to you the right way. But if I start rotating it, then you get an idea that there's something. This is a British DAC, whatever, audio thing. It's called the Mojo, really good product, by the way. Now, there's a problem with this. Although it's very fast and it's one of the first things that you learn, and it's easy to interpret, you have many big problems. Number one is that as soon as you have a lot of dimensions, then you get the infamous cursor dimensionality. So what is the cursor dimensionality? Is that everything is far away. This is one of my favorite quotes. In high dimensional space, no one can hear you scream because they are far away. Everything is far away. Everything is at the edges. So everything ends up being at the same distance for everything else. So you end up with a blob. And no matter what you do with that blob, no matter how you rotate it, how you look at it, this is what you get when you do PCA. You get a blob. And it suffers from scale. You don't get the same thing. If you imagine that you're measuring something, do you measure it in milliseconds? Do you measure it in seconds? Do you measure it in hours? You will get different scales, different pictures out of that. So it doesn't work in our case. So mind of the data scientist goes, so what do I do? How do I solve this problem? So you look for something that is not linear and you try to do something else. So there is this very interesting new method that's called UMAP, which is based on crazy mathematics, fuzzy categories and topology. And this is the same data. I'm showing you the first set is this. This is the same data mapped through UMAP. You get these beautiful islands that kind of look nice. Yeah, so UMAP is faster than other nonlinear methods. It's a lot slower than PCA. But the problem is that because there is a lot of non-linearity, it's difficult to interpret. But there's a couple of things that are really good about this. Number one is that it does not suffer from the cursor dimensionality. So things that are near, things that are far away, and it preserves local and global distances. And I'm doing a big introduction because in the end, it will all cascade into how we do this for our audiences. Right? So number one is we get the data, and of course I'm not able to show you Spotify data. I'm sorry about that. It's trade secrets are trade secrets, and they would kick me out if I tried to show something like that. And so, but bear with me, and I'll take you through the trip. So we get the data, we look at it. Now the good thing about looking at it this way is that you're already seeing that there is some structure to the data. And you don't see anything like points that are very far away, outliers and stuff like that. So you start understanding your data. And again, when you have tons of data, you cannot do this manually. You need heavy machinery to get these things. I'm just showing you 10,000, but let's say you want to run millions of points. It takes a long time and you need to be able to observe this. The problem with UMAP is that parameters are crazy, but I'm not going to take you over that. But again, mind of data scientist is how do I make this work in the right way? So let's put that aside and let's go into the clustering. So this is also another thing that you learn when you're studying to be a data scientist, machine learning engineer, or whatever. You learn clustering. Now, what is clustering? Clustering needs a few things that are very important to me. Number one is you shouldn't be wrong. So if a cluster exists, points should be assigned to the right cluster. If a cluster does not exist, then the point should be noise. If it's noise, it's noise. So the other thing is that it should be intuitive. If you're doing anything about your parameters and anything, you should be able to kind of understand what's happening. You don't know about the data, at least take control of your algorithm. And then you need to be stable. So clusters should be very similar if you run the same algorithm again. And if you sample a little bit, because maybe you don't want to run the algorithm, you're running out of memory or something. So you do sampling and you should get something very, very similar. And it should perform. It should be able to perform. So let me take you through the same data without colors. This is the same data I showed you before after running UMAP, but now we don't know the contents of the data. Imagine you're an alien and you're looking at this. And so I come here and I look at this and I say, okay, how many clusters are here? So very naive. I would go 1, 2, 3, 4, 5, 6. Although probably this might be 7, this might be 8, but let's say 6. So you've learned about k-means, which by the way is not a clustering algorithm, is a separation algorithm. And you put in the number 6 into the number of clusters that you want to achieve. You run this, and here's what you get. Very obvious, this is cluster 1, and very obviously this is cluster 2, and this is cluster 3, and then there's 4, 5, 6. This is wrong. This is absolutely wrong. And it will happen to you time and time again with k-means, because k-means has a random component where you start your centers somewhere. And so in this particular run, what happened is that there were 3 centers here. So next time I run the k-means algorithm, I will get a different result. And the other time I run k-means again, I will probably get a different result. So, and another thing, every single point is assigned to a cluster. In this case, it's okay, but it doesn't do the right thing. So I will go very quickly through the next slides. There's something called dbScan, which does trees and agglomerations, and it does a lot of things that seem right. And then you have on top of that something called HDBScan hierarchical. So it basically learns out of all the clusters that it's creating the hierarchy of that, and it decides on which are the best clusters according to some algorithm. And the problems that we get there. So again, bear with me, and I'm going through the mind of a data scientist solving this problem. dbScan requires 2 main parameters. One which is called epsilon, and the other one which is called minimum number of points. So epsilon regulates how far away I'm going to look. And the minimum number of points is, as the number says, the minimum number of points I want to see in a cluster. So what it does is it gets a point at random, and it goes like, are there any points within my epsilon of 3? Yes. And so I'll add them to my cluster. And then out of all these points, I'll repeat the process. Here, is there anything within 3 of distance? Yes, this. And so it starts adding all of this, and so on and so forth. This is not intuitive. I'll show you what happens when you change some of those numbers. You made a smaller epsilon, and the minimum number of points is 250. So now you get like 10 clusters, but they don't make much sense because these points look like noise. It's not able to agglomerate this. And then after a lot of experimentation, you realize that epsilon needs 2 and minimum number of points is 250. It works for your data. How do you get to know this? It's very, very hard. It requires experimentation. And I told you there was one thing that did this for you, which is HDBScan. So with HDBScan, if I say I want 500 points minimum, then it does the right thing. But wait, no, 250 does exactly the same. and 100 points does exactly the same. So as I told you, I need stability. I cannot get something that changes my solution every single time I run it, and it's stable with parameters. So by now, I found two things that work for me. I found a way to make dimensionality reduction work, and I found a way to cluster that works. So I'm halfway there. Imagine that now I get my data, my users somewhere. I've been able to look at this data. I've been able to find these little islands, and I have another algorithm that tells me which those islands are. So I've started separating my users into something. In this case, it was 100 digits, but it works the same for any other thing that you want to put it on. And so I have the beginning of something. I have data, I have the right way to do dimensionality reduction, and I have what I believe is a good way of clustering these users, because the other thing that I didn't mention is that no time did I tell this algorithm that I wanted 6 clusters. It will find the number of clusters that seem right under this situation. So no assumptions on my side about how many clusters I need. That's a very nice thing, because it can change. Okay, so now we come to the clustering interpretability, because again, I did this dimensionality reduction, which is nonlinear, and I did this clustering algorithm, which again is not linear, and humans do not think non-linearly. So we need to be able to interpret this. So old school, you do the profiling, you do the centroids, you look at the descriptive variables, and you look at the features you used, and you look at the distributions, and you need a human to do this. And there's millions of things. It's very difficult. It takes a long time. And also we're not understanding how good our algorithm is. So circle back into our machine learning. Now I have my original data, and I've done 2 things to my data, dimensionality reduction clustering. And so now I have these beautiful things called cluster 1, cluster 2, cluster 3, cluster 4, cluster 5, cluster 6, which are labels. So my problem that was an unsupervised problem became a supervised problem. I have labels now. I have data and I have labels. Now I have a classification problem. So I can actually train an algorithm to learn directly from my original data without doing the whole dimensionality reduction clustering again. I can get a machine learning model to learn that process, so that I can later use when new users come on board. Instead of having to do this all over again, I just predict with a machine learning model. So here's where XGBoost comes to the rescue. If you haven't used XGBoost, please do. There's a lot of buzz these days about deep learning, reinforcement learning, all of those things. They are fantastic. They've solved amazing problems, but not every problem needs deep learning. Sometimes more classical tools are very, very useful, particularly for analysis. And I'll tell you why XGBoost is really good. Because with XGBoost, you can get variable importances. Variable importances are wrong, are absolutely wrong. I can give you examples of variable importances that are absolutely contrary to what you would expect. Because of the way tree algorithms work, what happens is that there's a lot of importance towards the leaves of the algorithm against the root. And so I have an example where the algorithm is very, very simple. You get a prize if you're able to jump a hurdle and score a goal. Okay, jump a hurdle and score a goal. It's a simple and, very symmetric problem, right? It doesn't matter in what order you do. You score a goal and you jump a hurdle. It doesn't matter, right? And so the payout for that, for the, let's say you train an algorithm to try and understand that. And so jumping a hurdle should give you the same reward as scoring a goal. But because of the way it works, if the order of variables in your data actually make one variable be double the importance of the other. So it's wrong. But there is something that you can do with XGBoost, which is called SHAP. So SHAP values, if you haven't heard of SHAP values, leave this meeting, go read them about right now. It's just best thing since sliced bread with Nutella on it. It's amazing. You just get a lot of information. And if you're a data scientist, it helps you understand why your model works and what are the important variables. And if you're a user researcher, which is, you generally don't associate data scientists and user researchers, we do a lot at Spotify. You can tell stories about the data. So this is actually not Spotify data. Again, this is the Titanic data set. So it's why people survive or not the Titanic. So there's something about this, like if you were female, you are more likely to survive. Of course, your class of service was more, this is a high value of class of service, so you were in third class. So you drowned because you were at the bottom of the boat. And then your age was important. And if you look at this circle here, for these people, age was a lot more important than being female. These are babies. So ladies and babies first is a story that you can actually see with your data here, right? But if you were old, tough luck, right? And then there's this thing here, there's a number of siblings and spouses, and this group of people had the worst chance of surviving. So if you had a lot of siblings and spouses, then you waited for them. And you didn't get to the lifeboats and you drowned. Sorry, it's horrible, but you can tell the story here, right? And could you tell the story with variable importances? No, you could not tell the story with variable importances. And so with this, you can understand what's going on. And I'm making these very dark jokes about poor people drowning, but imagine that you're looking at this and you see that, and you want to understand the problem, and you see that being male is absolutely important, and then being female has zero importance, or that the important group is your age between 30 and 50. You see that there's something wrong with that. You internally understand there's something wrong. So you're able to understand that there's bias in the data as well. So let's say you're working with transactions in a banking environment, and you see that race comes at the top. So what's going on here? My algorithm is picking up the bias in the data. If race is the most important thing, then the data is biased against race. And so I need to try to mitigate. True story, I was doing a model on understanding if a person was going to go to a live concert. Funny, I was getting amazingly good results. And an amazingly good result with real life data is a big red flag. you should not get a 96% accurate model. And when I looked at this, I saw that it said something like country UK, absolutely important for a negative. And so I looked at the data because I have data about 100 and something countries, and why does UK stand out? We had miscoded the data for the UK, and so it was all no's. So of course we were getting UK correct. The model was saying, no, you're not going to live concerts. And so I removed country because of course I wanted to understand if the model worked without the country. And this one here became email domain. And like, why email domain? And I go and look at the email domains, and of course there was a .uk and sky.com and those things, which were a proxy for data. So it helps you understand your biases. It helps understand that there's something wrong with your data, but it also helps you tell the story of what's happening with your data. That's really, really good thing to do. And then you get other things like you can look at each variable separately. You can look at what happens with age. There's this bump here happens at the 30-something years old and third class. So it was workers in third class pushing people down the stairs, probably trying to save themselves. But then, okay, 3 pieces now, right? We did dimensionality reduction, we did clustering, we have a machine learning model, but now we want to understand it. And so today I showed you that there were 6 clusters, but there were probably 8. So how do we understand if that is something? So what happened is that HDBSCAN gets this hierarchical idea. And so what if we could remove the hierarchy and look inside that hierarchy? Because if we're trying to understand audiences, what will happen is that we find this big audience and we want to understand if there's subgroups of that audience. So let's say we find rock-like users, and then maybe we have the indie, the metal, and the classical rock and roll kind of subpopulations, and they might behave slightly differently. So, well, and this is something I found that I discussed with the creator of UMAP, is that here there seems to be some structure. So what I did was get only the data belonging to this cluster and put it back into my algorithm of dimensionality reduction, clustering, and so on. And this is what I found, that this thing that looked like an island actually separated into 3 in different runs with different samples. And these are the populations that I found, the 3s, the 5s, and the 8s. So the original cluster was 3 horizontal lines somewhere, and some rounded left and right things. So it learned to separate this. So then went like, does it happen somewhere else? Does it happen in this cluster that does not seem to have any structure? Yes, it did. It's a cluster of zeros. And if you look at this, it's round zeros, slightly less round zeros, very thin zeros, and zeros slanted to the right, and slightly rounder zeros slanted to the right. This is amazing. If you can get this level of detail without actually having to do a lot. You basically put your data through this grinder and you get all of this information out of this. And you can understand why by doing the interpretation. So here's the picture again. We did the high dimensionality user level. We did UMAP to get the low dimensionality. We did this recursion, and then we were able to interpret. And then we can output. And we have a machine learning model that has learned all of this process. And so whenever we get a new user, we don't need to retrain all of this. We just put it through our machine learning model that learned to do all of this, and we get an output, and we understand roughly where this user belongs with some sort of probability. And we can use it for different things. The same methodology can be used to understand user traits. Does this person prefer sporty things? So you can use all of this to really dig into our audience. And most importantly, the assumptions that we made are only the assumptions that exist in the data that we use. We did not impose anything on the data, except our selection of the data.
Gustavo, I have a question. So
yes.
Do you essentially reduce disinformation? So in example of Spotify specifically, would you look for that granular information onto those different types of people that listen to those different types of music? So, because the predictability of what would essentially, what they would enjoy then, does that increase if you get it more granular, or?
So what we've seen is that if you take a look at behavioral data, for instance, and that was an assumption I made some time ago, is that if you look at people during their first day, it's when you just get the app for the first time. Although a lot of people now don't get to Spotify for the first time, they've seen Spotify a lot. But let's say you get Spotify for the first time. So you have your preconception of what you want to do. So during your first day, you will click on stuff, you will explore, you will try and search to see if your band is there. You will do some things, or other people will go and immediately create playlists and so on. And we discovered that if we look at those behaviors during the first day, we can predict quite well if that person is going to stay on Spotify or not, or if they did not understand the proposition of Spotify. So we found, for instance, that there was a blocker when people were signing. By looking at this, there was this cluster of people that got into Spotify and abandoned within a few minutes. And we looked at it, and it's basically they did not understand what was going on. We were making them select artists and doing all the onboarding. So they just wanted to listen to music. They needed a radio kind of thing, right? So we added a button to let people skip that part, and suddenly the cluster started disappearing. And so we start understanding these sort of things where, and then the next question is, how granular do you want to go, right? And I'm a factory of bad analogies, and I think that clustering is comparable to juggling. And so everybody can learn to juggle 3 balls in the air. It takes about 15 minutes. Honestly, it takes about 15 minutes of practice to learn to juggle 3 balls, at least a couple times. 4 balls, it takes a while longer. Not many people can do 5. 15, only one person in the world did like 17 balls for just 1 round. And imagine that you're a data scientist, so your job is to understand the data and tell stories about your data so that decisions are made. And so imagine that your stakeholder is the juggler, and you just handed this person 10 balls. If they're very good, they would be able to do it, but most of the times they will not. So you need to strike a balance, and that granularity is something that you decide together with your stakeholder. That's a very important thing to do. You always need to have an audience in mind, and that audience in mind is not you, the data scientist. You would love to have 100 clusters and go as deep as possible, but decisions need to be made, and you need to be able to maintain all of this. So, yeah.
Interesting. Thank you.
So, of course, there are more things about this. There's something I'm working on which is called consensus clustering. which is basically repeating this process many, many, many times so that these clusters become really, really stable. And so we are certain that the clusters that we found are not a fluke. And then, of course, and this is something that I just want to show you, these are all the parameters and all the things that you start looking at when you're looking at these things. So there's a lot. So in the mind of a data scientist, and I'll stop now sharing. So in the mind of a data scientist, there are a lot of steps that you need to take. And to me, the important thing is that every single time you need to do the right thing for the right reason. And I probably rushed through this presentation. Sorry about that. I planned it for a bit longer, but I wasn't looking at the watch. So we have a lot of time for Q&A, which is good. Or I can go over some of the finer detail if anybody wants to ask.
I mean, we can give people a few seconds if anyone has any questions. Alternatively, would you be open to people getting in touch if I either connect? I'm sure people could connect with you on LinkedIn.
Yeah, no problem.
Get in touch otherwise.
Absolutely no problem. And of course, there's always we're always interested in getting people interested in what we do and why we do it. And we're always hiring. That's the other. Sorry for the shameless plug. We're always hiring. We're always looking for talent. And right now at Spotify, we have this work from anywhere policy. So the world is your oyster. If you are within a country where we have a Spotify legal representation, you probably can work from there remotely. So
this opportunity. So this is being recorded as well. So we will distribute it to our other students as well. Some of them did have exams and coursework and stuff. But as they will listen to it, maybe you'll get a few CVs through.
Yeah, I'm not the right person to get CVs. There's the Spotify jobs, and there's also the students page, because we also have internships that are a very interesting modality, because you know, real life data and real life problems are completely different from what you usually get in research, and you spend a lot of time just discussing data. And then you get to the fun part, which is actually working on this. And I showed you all this diagram and this, I spoke about it for about half an hour. It took over a year to come to the conclusion that that was the way to do it and to get the right data and to do it the right way. Luckily, we are at Spotify, where we have the time to do those things and we have the resources. And sometimes we can do these experiments and we can send out surveys and try to understand. We did this with surveys. And in no point, I think nobody in history has done an analysis of over 100,000 responses to a survey. Over 100,000 responses to a survey.
It's information that's powerful, isn't it? I had a quick question actually. In terms of like the competition, so is every sort of a music streaming company that is doing this, are they all developing techniques like that? Are they all looking at the data in a similar way? Is it almost like an industry practice, or is this something quite specific to Spotify where others do something else? One company that comes to mind is, I believe, Deezer. A lot of people probably laugh and call me, you know.
Yeah, so I don't know, honestly. I guess they are looking at the data somehow. But
Let's hope.
let's hope. But of course, within the music industry, there are several things that you do with machine learning and AI. So recommender systems, or going through multi-armed bandits and all those crazy names. So what I wanted mostly to show right now is the process that you go through from a question, like if we know how, if you know we have these people and this data, what are the audiences that we have? Do we have a main audience? Do we have a secondary audience? How many different types of audiences do we have? What is the difference between them? How can we target them? What makes them tick? But also with every decision you do by design and the experiments you run the risk of running into some ethical problem and introducing bias. And so by looking at why we're making the decisions we make, or by looking at, let's say we run an experiment, and instead of looking at the overall result, you look at the different subpopulations. So you can try to understand which population moved your experiment positively. And most importantly, which population have you left behind? Which population is actually hating the change that you've introduced? Because we've seen that happen. In some countries, we introduced a different type of licensing, and which was some sort of on-demand. Nowadays, when you jump into Spotify, you always have trials. But at that time, trials were not a big thing. So we're trying to understand if trials and on-demand was a good thing. And so we tried an experiment and in a country. And one of these subpopulations moved the retention after 30 days by 20 percentage points. 20 percentage points is the craziest number we've seen in an experiment. You are happy if you get 0.1 percentage point change. So we made these people 200 times more likely to retain just by giving them on demand.
Yes.
And we moved the whole experiment, like it was like 3 points, but this population was like 20%. So,
I guess it's not the case, because my question was, you explained it really well. I was going to ask, how can it be a problem of ethics if it's numbers, right? Numbers shouldn't be unethical, as it were. I guess in the situation where you have to decide between implementing something one way or another, that's when you run into those problems.
But you're always, right? You always have an ethical problem, because you decide what data you use and how you gather that data. And every single decision you make, you're going to be, because of the scale that you're working in, it's going to affect a lot of people. We affect over 300 million people a month. Over 300 million people a month. So what if our choice is culturally insensitive at some point? Or what if, who are we leaving behind is something that we're always asking ourselves. Because we want to have the whole, our mission is to get as many people as possible involved, and so that they use our app and we generate revenue so that we can pay artists. And actually, it's not us, we don't pay artists, but that's a different story. Because I know that there's a question always, there are pages that explain how the industry is paid through streaming, and I'm not going to even.
Let's not get into that.
but every time you make a decision, you run an experiment. Even again, the way you choose to represent your data might include some bias. It might. Let me tell you this. I'm looking at age. Right? And instead of using age, I decide to put buckets of age, right? Under 18, 18 to 25, 25 to 35, 35 to 50, 50 onwards. So I decided that by 35, you're an old geezer. All right?
Interesting.
But it is actually, I put you in a bucket together with all those people. Right, but when you put the age, then you realize that the model is breaking it at 21 years of age, and 34 years of age, and then 34 onwards. And basically it's pre-college, early adult life, teenage kids. You have teenage kids already. And so that is the break that makes sense, not the one that you impose into your data. And every single time it's like that.
I've got a question. So it's anonymous attendee saying, thank you for the wonderful clustering logic. My question is, can we, I think that one, can we possibly, I think,
possibly, is it possible? Is it possible
Yeah.
to treat museum exhibits the same way as songs do? Of course. You can always try these kind of things. And now, how do you, it depends on what you measure about the exhibit, right? So are you, I don't know, foot time, stare time, or style, or you input all of those, and then you see, okay, maybe you want to understand that there's some pieces that generate more foot traffic, and so maybe you want to spread them out across the museum, so you get foot traffic across all of the museum, or you look at characteristics of your exhibits, like color palette and years, and then you do this kind of same thing, and then you will find that some clusters appear. Now, one thing with clustering that I forgot to say is that there is no right answer. There is no right answer. You don't know beforehand what you're going to get. So you need to decide if that makes sense to you as a subject matter expert, right? Because let's say you are at a museum and you decide to have the browns, the whites, and the greens, and maybe that's an interesting thing. Or sculpture, old Greek sculptures, modern Greek sculptures, and Roman interpretation of Greeks and Renaissance, and so on. So do you want to do that? Do you want to put them together? Again, the clustering that happens depends also on the data that you use. But yes.
Interesting question. I think if we have no more questions from the audience, and this is the last few seconds as I draw to a close for anyone that wants to pop a last one in, essentially, just a last prompt, we'll slowly draw everything to a close. Thank you so much for coming along, Gustavo. It was a really interesting presentation. Thank you, everyone else, for obviously attending and coming. So this concludes AI Week. The recordings of all the sessions will be available to you. Those will be sent out to all of our attendees. We'll try to get that out next week. And as we have no further questions, I believe, would you like to throw in any last words, Gustavo?
Just thank you very much for showing up. I know it was the last session, so you're probably tired by now, and after 5 days. But please reach out if you come up with any questions, or just if you want to connect. I'm open to chat. I like all things data science, so please reach out.
Awesome. Thanks a lot. Thanks a lot, everyone.
Thank you. Bye.